Hello and welcome to lecture 40 of the course Computational Complexity. So we have so far we have seen various various complexity classes based on the circuit complexity, such as p by poly and uniform variants of those, and we have seen how they relate to whatever we have already seen so far, such as polynomial hierarchy, for instance, right? We have also seen how much size is required to compute certain functions, languages, etc. Today we are going to see two sets of circuit classes called NC and AC, which are actually both of which are contained in P by poly, but are more fine grained in their definition, right? So let us define NC or NC superscript I. Okay, so NC superscript I are this class of languages that can be decided by a family of circuits that have polynomial size. The circuits should have polynomial size and the depth should be log n power I, okay, and must use AND, OR and NOT gates. So far I think we have mostly been talking about circuits restricted to AND, OR and NOT gates, but I am just restating it. And the most important thing is that these gates in the case of NC must have fan in equal to at most 2, right? So obviously NOT gates have fan in 1, so AND and OR cannot have fan in bigger than 2, right? So this is NCI. So NCI means so when I increases you get more and more depth, right? But all of this is limited to polynomial size circuits. And ACI is a similarly defined class. Everything is the same except that the only difference being the AND gate and OR gate can have unbounded fan in. Okay, the AND gate and OR gate can have unbounded fan in. So this is the main difference. So here they have fan in 2 in the case of NC, but in the case of AC they can have unbounded fan in, right? And unbounded really means it is enough to have polynomial sized fan in, because or fan in to be polynomial in n, because size is itself polynomial n. So practically the fan in could be polynomial. Okay, so now let's see. So this is ACI and NCI. So both of which have polynomial size, log n to the I power log n power I depth, and is constitutes of AND gate, OR gate and NOT gate. In the case of NCI, we said that the AND gate and OR gate cannot have fan in more than 2, but in the case of ACI they could have unbounded fan in. Okay, right? And the class NC, right, just without any superscript, is just nothing but the union of all the classes NCI, and similarly the class AC is the union of all the classes ACI, right? So it's an infinite union. So just to so Nick Pippenger used to work on these kind of circuits, circuit classes a lot. So NC was informally, or the name NC was stood for or stands for Nick's class. So this was named by Steve Cook in the honor of Nick Pippenger. And in turn Nick Pippenger named another class SC and he called it Steve's class in the honor of Steve Cook. So they did this kind of mutual friendship kind of fun thing during that time. So AC does not stand for a name, it stands for alternating class. So because it corresponds to an alternating Turing machine class. Okay, so that does not have an interesting story like this Steve's class and Nick's class, right? And we will not be seeing the Steve's class during this course, right? And actually there is a hierarchy between all these NC classes and AC classes. So let us see what is that. So one thing that you may have already observed is that as you provide more depth, you get more power, right? So each NC2 will obviously be contained in NC3, which will be obviously contained in NC4, because whatever can be done in NC4 can certainly be done in NC3, and whatever can be done in NC3 can certainly be done in NC2. So NC0 is certainly contained in NC1, which is contained in NC2, and so on. Same thing holds for AC as well. right? So AC0 is contained in AC1 and so on, right? However, how are these interrelated? The first thing that you may note is that NC and AC are exactly the same, except that AC allows unbounded fan-in. So this tells us that whatever can be done in ACI can certainly be done in NCI, because whatever can be done in NCI can certainly be done in ACI, because if you have unbounded fan-in, you are not bound to use it. You could just use them as fan-in 2 gates, right? So NCI, so I'll just write down, NCI is contained in NCI plus 1, this is easy, and ACI is contained in ACI plus 1, this is also easy, right? NCI is contained in ACI because more fan-in equals to more power, right? And finally, ACI is actually contained in NCI plus 1. Okay, so this is probably the only interesting part. This is because what does AC have that NC cannot have? It is the unbounded fan-in and OR, right? So suppose an AC circuit had a fan-in, had an AND gate, right? Had an AND gate, right? That took poly N fan-in, right? What we can do is we could replace this gate. We could replace that with something like this. We could replace that with a tree of sorts, something like this, a tree of fan-in 2 gates, which would actually be computing the AND again, right? So we could replace it with a tree. And what would be the depth of this tree? So the depth of this tree will be logarithmic of polynomial n, so which will be depth log of polynomial n, which will be actually some order log n, right? So because simply polynomial n is upper bounded by some n power k, so it is just k log n. So by replacing unbounded fan-in gates with O log n depth tree. So basically the blow up of the depth, so polynomial size remains polynomial size because log n doesn't change, but the depth, there is a depth blow up of log n. So the ACI circuits have depth log n power I, but then there is a further blow up of log n, so log n power I multiplied by log n, it is log n power I plus 1. So what we get is a circuit with polynomial size where the gates are AND or are not with fan-in 2, but where the the depth has increased from log n power I to log n power I plus 1. So it is NC I plus 1. So now summarizing all this, right? Summarizing all this, we could just write it like this. So we have NC0 contained in AC0 contained in NC1, AC1 and so on. It's a chain. And since we have this nice relation, it also turns out that these two classes defined above, NC and AC, they are virtually the same thing, because if it is an NCI, then it is an ACI as well. If it is an NCI, yeah, that is an ACI as well. If it is an ACI, it's an NCI plus 1. So when you take the infinite union, they are both the same. So basically NC is actually equal to AC, right? And this hierarchy, one interesting point is that I want to mention is that NC0 is not very interesting. Okay, so maybe I'll just make some space here. NC0 is not very interesting. It's not an interesting class. This is because you are allowing polynomial size and constant depth alone in constant depth with gates of fan in 2. So you can only use 2 power d inputs for a certain output. Right? Each output is a function of only 2 power d inputs. So it is only looking at a constant number of inputs. So this is not very interesting. Not much can be done in using this kind of a setup. So NC0 is not very interesting. For instance, even simple things like AND gate on n inputs is not in NC0. But AND gate on inputs is certainly in AC0 because it is you can just use that one gate alone, right? So this inclusion is strict. NC0 is a proper subset of AC0. We also know that AC0 is a proper subset of NC1 because there are languages which we will see soon. Parity, for instance, which is in AC0 but not, sorry, it is in NC1 but not in AC0. And what is interesting is that the rest of all the inclusions, right, all these are open. We don't know if the remaining inclusions are strict or proper or otherwise, or are there two classes that are equal, right? So this is something I want to say. And like I defined in the previous lecture, you could also define log space uniform NC and AC, right? Whatever I said holds for all the, whatever I said so far holds for all the NC and AC languages. But now let us focus on log space uniform NC and AC. So from now on we will just stick to log space uniform versions of NC and AC, okay? Which means that in addition to what we have defined already, we require that the circuit family must be uniformly generated by a log space algorithm, right? So given input k in unary, output, there should be log space algorithm that generates a circuit for inputs of size k. Okay. So now let's see some examples, and after which we will see some. So this examples will give us a general idea, and after these examples we will conclude and summarize. Right. So the first example is parity. Okay. So parity is just simply, if you have n inputs, is a generalization of XOR, right? If you have n inputs, input bits, parity is 1. So parity of x1, x2 up to xn, this is equal to 1 if an odd number of input bits are 1. Odd number of xi are 1, and it is 0 if even number of xi are 1. Okay, so that is parity, and this is in NC1, which means we are allowed log n to the 1 depth. Okay. So let us see why that is. So notice that we could make a parity gate. Let us say we make a parity gate and we denote it like this. So this takes two inputs, let's say x and y, and outputs 1 if exactly one of them is 1 and 0 otherwise, right? So this is a single parity gate, and this can be constructed using a, you can construct this using a constant depth circuit, right? You could just use AND gate and OR gate to construct this, right? So you can verify that. And now using this single parity gate, you could build a parity n gate. So you could have x1, x2, x3, x4 and so on, xn minus 1, xn. So you could have some construction like this. So finally culminating at the output. So this has depth order log n because each parity gate has a constant size. So this, the way I have drawn it, it is not a NC1 representation because I have constructed using single parity gates. But then you can replace each single parity gate with a small circuit that uses only AND gate and OR gate of bounded fan-in, right? You can work that out. So this is certainly possible. So where I'll just perhaps write that each parity gate can be constructed by a constant size circuit using AND, OR and NOT. Okay. So this is and now the depth, if you measure, there are n inputs, the depth is log n, right? And this has depth log n. So this is a, and you can verify that this indeed computes the parity function. So if you just cascade the 2-bit parities as a tree, then you will get the n, indeed the n-bit parity. So parity is in NC1, and what is known, which we will see later, is that this was somewhat of an important theorem, that parity is not in AC0. Okay, so this is an interesting and involved proof, perhaps one of the longest that we will see. So this shows that this containment here is strict. We have a language that is in NC1 but not in AC0. Right. The next thing is Boolean matrix multiplication, and this is in AC0. So let us see what is Boolean matrix multiplication and why this is the case. Right. So suppose A and B are 0, 1 matrices. Suppose this is A, suppose this is B, n by n matrices as well, 0, 1, n by n matrices. And what is Boolean matrix multiplication? So in a standard matrix multiplication, we would take the, let's say, one row of A and one column of B, such that we will add up the like A11 will be multiplied with B11 plus A12 will be multiplied with B21 and so on. Right. So what we will have in a usual multiplication is the ijth entry of AB will be summation of k equal to 1 to n, right, of Aik multiplied by Bkj. But Boolean matrix multiplication means we will replace summation with an OR and we will replace multiplication with an AND. Okay, so just to remove confusion, I just wrote this for explanation. Just to remove confusion in the notes, I will just erase this. Right. So this is the Boolean matrix multiplication, and we can do it using AC0, which is a class of circuits with constant depth. Right. AC0 means constant depth, but allowing unbounded fan-in gates. So why is that? So we could, so I'll just show you how to compute AB, the product, ijth entry of the product, right? So we have AI1 and B1J, we have AI2 and B2J, and so on up to AIN and BNJ. So first we have AND of all of this, right, and then we have a giant OR of all of this. And this is the output. So clearly this is a constant depth polynomial size circuit, right? So it's a constant depth polynomial size circuit, and this correctly computes the ijth entry of the product. So hence Boolean matrix multiplication is in AC0. The next thing I want to talk about, so since it's in AC0, it also follows that this is also in NC1, right, because AC0 is contained in NC1, right. The next thing is graph reachability. So we also called it, I think we also called it path while we were discussing space complexity, right. This was kind of the canonical language that captured that was kind of complete language for any space bounded complexity class, right. So we had a directed graph G and we had two vertices S and T. Is there a path from S to T, or is T reachable from S? This was the language. So we will see that this is in AC1, right. So we will see that this is in AC1. Let's see how. The key point is that we could use what we just saw, the Boolean matrix multiplication. So let us first define the something like the adjacency matrix. Okay, so we will call it A. So A is the ijth entry of A is 1 for two cases. One is that if I is equal to J, right, that means all the diagonal entries are 1, and 2 is if there is an edge from I to J. So if there is an edge from I to J. So in these two cases, ijth entry is 1. Another way to interpret A is that can you reach J from I in one or less number of steps. So one step means there is an edge from I to J. Less means how can you go from I to J in 0 steps if the other possibilities I and J are the same place, right. So you can, so the ijth entry of A is 1 if you can go from I to J in 1 or 0 steps, 1 or less number of steps, otherwise it is 0. So the claim is that this is something that can be verified. There is a path from I to J of length at most L, okay, length at most L, if and only if you take the lth power of A and look at its ijth entry, if that is 1. So there is a path of length at most L from I to J in the graph G, if and only if you look at the lth power of A and look at its ijth entry, it is 1. So this can easily be proved using induction. So I will just give you a high level idea, right. So by definition, the claim is true for L equal to 1. The way we have defined A, it is true for L equal to 1. A is A power 1, and the way we have chosen the entries for A, it is satisfying this requirement. Now let us see what happens when you take A squared, right. So what happens when you take A squared? So when I say power, lth power or A squared, I am talking about Boolean matrix multiplication there, right. So A square is basically or k equal to 1 to n aik and bkj, right. This is what the ijth entry of the A square. So it's not bkj because it's not A and B, it is akj. So this will be 1 if there is, so aij equal to 1 if and only if there is a k such that aik and akj are both 1. So, which means we can reach from I to k in one step and k to j in one step. So, which means you can reach I to j in 2 steps. So, notice that in the case, so that is exactly what we wanted, right. A squared, the ijth entry of a squared is 1 if and only if there is a path of at most 2 steps from I to j. So, this is what we wanted to verify. Again, this if you elaborate it and use an inductive proposition, you can prove this claim. I am not writing the details, but you get the idea. So, now we will say that GST is reachable or GST is in path if and only if there is a path of length at most n from S to T, right. So, the question is T reachable from S. So, and the length of the path is actually at most n, in fact it is actually at most n minus 1, right. So, a power n minus 1 st equal to 1. So, now all that remains is to compute the n minus 1 entry, n minus 1 power of a, and then look at the stth entry. So, we have seen how to compute a product of two matrices using an AC0 circuit. Now, we could repeat the same idea. You could compute a squared using that AC circuit, and then a power 4 using a squared as input, and so on. And if you use the ideas of this repeated exponentiation, repeated squaring for the exponentiation, we could compute a power n by using at most 2 log n multiplications. Okay, so you can, again, this is something that is not very difficult to see. This is something that you can work out. Okay, so again you can work this out. How can you compute a power n using at most 2 log n multiplication? So, you compute a squared, a power 4, a power 8, and so on, and then you do something. Okay. So turns out that's all that you need, right? So, you need to compute a power n and then look at the stth entry. So you will use an AC0 circuit 2 log n times, and perhaps the output of one is used in turn as an input of the other. So, AC0 circuit multiplied by 2 log n means the depth can become constant from the constant size circuit. It can become order log n size circuit, order log n depth. So, this could result in order log n depth increase by stacking of AC0 circuits. And that gives us an AC1 circuit, and that is what we stated at the beginning. And in fact, I would also say that this means that it is in NC2 because AC1 is contained in NC2. And in fact, I am not saying it explicitly, but it is also true that all these examples that we are doing, all of these are actually uniform NC or AC, because there is a very clear structure of these circuits, and this can be generated using a log space algorithm. And finally, I just want to take up one more language or one more operation, which is addition, and we will show that addition of two n-bit numbers is in AC0. Okay, so why is that the case? So let a and b be the two n-bit numbers. A be an minus 1 up to a1, and bn be bn minus 1 up to b1. Let the sum be denoted by d. Okay, d, and the sum could have one more bit. Right? It cannot have more than one extra bit. So let it be dn plus 1 dn dot 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 d1. So when we add two bits or add two binary numbers or add two numbers in general, we could have, there is sum, and we also could have the carry bit. Right? So when you add a1 and b1, it may generate d1, and it could also generate a carry bit that goes to the next column. So let Ci be the carry bit that enters into the ith column, right? Ith carry bit meaning, carry bit reaching the ith place. Not generated from the ith column, but reaching the ith column. We will just say column instead of place, right? Okay, so we call it Ci, right? So now let us, what is easy is to look at the sum. So the sum at the ith bit is basically, you have the sum at the ith bit is, you have Ai, you have Bi, and you have a carry coming up from the previous location, and you need to output the sum. And in fact, the sum is just a parity function on these three quantities, on Ai, Bi, and Ci, right? So the sum is merely a parity of these three quantities. So Di is 1 if and only if if and only if one of Ai, Bi, Ci is 1, or all of Ai, Bi, Ci is 1. If 0 or 2 of them are 1, then Di is 0. If 1 or 3 of them are 1, then Di is 1. So I will say Di is 1 if and only if either 1 or 3 of Ai, Bi, Ci are 1s. So it is a parity function, right? So again, parity function, we have already seen how to write that using a constant size circuit. So again, this is a constant size circuit, so this is straightforward, right? What one may wonder, or one may think is the difficult part is the carry, because let us look at the carry at the nth bit, right? The carry Cn. So the carry at the nth bit arises as a result of the carry from the n-1th bit addition, which arises as a result of the carry from the n-2th bit addition, and so on. So one may be tempted to think that there is an n-1 or n level dependency. An and the Cn depends on an and an-1 and bn-1, which in turn depends on an-2 and bn-2, and so on. So one may think that there is a dependency that goes down to n levels, right? So one may be tempted to think that the depth of a resulting circuit may be actually order n, or linear in size, right? Or linear in depth. Right. So this will mean that it cannot fit in the NC hierarchy or AC hierarchy, because all our NC or AC hierarchy, we have the depth equal to order log n power I, right? So this cannot be linear. However, it turns out that we don't need that. We don't need an dependency, order n dependency. So let us see why. So when is the ith carry bit equal to 1? Okay, so let us see. So C1 is 0 by definition, because A1 and B1 are the least significant bits, so there is nothing coming from the 0th carry, right? So C1 is 0. Okay, and Ci plus 1 is 1. When is Ci plus 1 equal to 1? It becomes 1. Okay, Ci plus 1 is, so I will maybe write down here. Ci plus 1 is the carry at the Ai plus 1 and Bi plus 1. So let us look at what would have happened at Ai or Bi that resulted in Ci plus 1 being 1. It is possible that Ai and Bi are both 1s. If Ai and Bi are both 1s, certainly Ci plus 1 equal to 1. Right? Other possibility is Ai and Bi are not both 1s, but at least one of them is a 1. Let us say one of them is a 1, but then they got a carry from Ci minus 1, which means they got a Ci minus 1 as a carry. And how could Ci minus 1 have come? That could have come because perhaps Ai minus 1 and Bi minus 1 are both 1s. right? So I have captured these two things over here. Ci plus 1 equal to 1 if both ai and bi are 1s, or one of ai and bi are 1 is 1 and both ai minus 1 and bi minus 1 are 1s. Now you could take it to the next level, right? So another possibility is that both at least one of ai minus 1 and bi minus 1 are 1s, but they got a carry ci minus 2. And how did they get a carry? Because both ai minus 2 and bi minus 2 are 1s, right? So you could write that as a next step. Sorry, ai minus 2 and bi minus 2 are 1s, and at least one of ai minus 1 and bi minus 1 are 1, and at least one of ai and bi are 1s. And notice that these conditions are also important. Suppose ai minus 2 and bi minus 2 are both 1s, you get a carry ci minus 1, but both ai minus 1 and bi minus 1 are both zeros. So then that carry does not propagate. So for the carry to propagate, at least one of ai minus 1 and bi minus 1 has to be 1, and one of ai and bi has to be 1. And now you can keep generalizing this, or we can keep extending this. And the last possible situation is that ai and bi are both 1s. Sorry, a1 and b1 are both 1s, and for the rest at least one of them are 1, so the carry keeps propagating. So a1 is 1 and b1 is 1, and then for a2 and b2 at least one of them is a 1, a3 and b3 at least one of them is a 1, and so on till ai and bi, right? For all j, aj and bj are both aj and bj at least one of them are 1 for all j equal to 2 3 1 2 3 4 5 up to I, right? So this is how the carries can occur. This is the only situation. So now let us write an equation for this, a Boolean expression for this, right? So ci plus 1 is equal to a big OR, right? So OR is basically we are trying to, whatever we have written over here, this big red expression, we are trying to write it more crisply over here. So it's an OR of all these things. So what is the so maybe it will help look at the k equal to 1 case, right? So when k equal to 1, we have a1 and b1, so both of them should be 1, so which is actually the last row over here, a1 and b1, and I think there is a small mistake here, so it should actually be k plus 1, I think. Right, so a1 and b1 are both 1, and then a2 and b2 at least one of them has to be 1, and then followed by a3 and b3 at least one of them has to be 1. So maybe I'll just write one more, ak plus 2 or bk plus 2, and so on, right, and so on till ai or bi, right? This is when k equal to 1, and k equal to 2, it starts from a2 and b2 should both be 1, and then everything from that point till I should be, at least one of them should be 1. Anyway, you can verify that this expression for ci is the correct expression, right? This expression that I have enclosed, and now it's very straightforward to see that this expression can be evaluated using a constant depth circuit, right? So you have a big OR, but that's okay, we are allowed unbounded fan-in, and in fact there is a big AND inside each of these ORs, that's also okay because it's unbounded fan-in, and inside this AND it is all small circuits, it's all two-way fan-in 2 items. So we will get a depth 3 circuit for this, right? So this can be evaluated using a depth 3 circuit, so constant depth circuit, ANDs and ORs. So it is in AC0, which is what we had claimed. So addition is in AC0, Boolean matrix multiplication is in AC0, right? Graph reachability is in AC1, and parity is in NC1. And I would like to just summarize what we know so far, or some of which I'll just give a brief outline um, about these classes and how they relate to some of the classes that we already know. So one point is AC0 is contained in NC1. That NC0 is not interesting, so I will not write about that. And this containment is strict, AC0 contained in NC1. And NC1 is actually contained in log space. This is because, so maybe I'll just write in, this is because, so again this is only for, this is when I am assuming that all these classes where applicable is log space uniform. So log space NC1 can be simulated by a log space TM. This is because the generation part can be taken by a log space Turing machine, because the generation is in log space, and then the circuit evaluation, once you generate it, even that can be taken care by a log space Turing machine. And combining these two, the generation as the evaluation, takes some work, but we saw the idea at the beginning of space complexity, how you could combine a space bounded reduction, right? You had this idea about running the how you could combine two log space bounded machine to get a log space, how space bounded two space bounded machines can be combined to get a space bounded machine, right? You will start the second machine, and whenever you need an input from the first output, from the output of the first machine, you will then run the first output machine, and so on. So that's the idea over here. L is contained in NL, which something we know. NL is contained in AC1. This is because of something that we have seen already. Graph reachability is in AC1, and we saw that graph reachability is kind of the canonical standard complete problem of NL, right? So this is because path is in AC1, path or reachability. And then it is just the NC hierarchy. AC1 is contained in NC2 and so on. So then I am writing everything is contained in NC, right? Everything is contained in NC, and the uniform NC is contained in P. Okay, so this is because uniform NC is contained in P. So in the previous lecture, I said that any log space uniform family is contained in P, or all the log space uniform family is the same as P. But then in the case of NC, you have more restrictions. You cannot guess any circuit of using a log space, or you cannot generate any circuit using a log space machine, because we have other constraints about how much the depth should be log n power something, right? So it's only a containment, it's not inequality. And the rest are something that we already know. P is contained in NP, which is both contained in P space. So this is some collection of some classes that we already know, how they relate to each other. Many of these we don't know still which containment is strict or which containment is proper. We know that NL is, so many containments we still don't know. We still don't know if they are proper. So we know that NL is a strict subset of P space, and I think that is about it. NL is a strict subset of P space. This is due to space hierarchy. And so that means that at least somewhere in this chain there should be two classes that are nearby, but they are not the same. It cannot be that everything is equal. If everything is equal, then NL will be equal to P space, which we know is certainly not true. but we don't know which one. Right, I'm just trying to see if there is any other things that we know, any other strict containment that we know. Seems like no. I think everything else is still open. And I think that's all that I wanted to say in this lecture, lecture 30. So we defined the NC hierarchy. NC is the class of all languages that can be decided by polynomial size or order log n to the power I depth circuits using AND or NOT gates, where AND and OR gates are have fan in 2. ACI is exactly the same, but we allow unbounded fan in. Then we saw this hierarchy between NC and AC, and we saw what is uniform NC and AC, and from then on we only focus on uniform NC and AC. So we saw that parity is in NC1, and I mentioned that parity is not in AC0, so that is why AC0 is a strict subset of NC1. We saw that Boolean matrix multiplication is in AC0, graph reachability is in AC1, and we also saw that addition is in AC0. And then finally we summarized about some of the classes that we have already seen. And this completes week 7. Just to summarize week 7, we saw definitions of circuits, we saw circuits that require certain size, or we saw that most functions can be computed by exponential size circuits, and in fact most functions require exponential size circuits, right? And then we saw the class P by poly and what that is capable of. We saw P is contained in P by poly, but then they are not quite the same. Then we saw Karp-Lipton theorem, which says how NP is related to P by poly. It's unlikely that NP is contained in P by poly. We saw Mayer's theorem about exponential time, how that relates to P by poly, and then Cannon's theorem, which said that there are languages or functions that require arbitrarily large size circuits or arbitrarily large size polynomials in the polynomial hierarchy. And then we saw Turing machines that take advice, and finally we saw the NC and AC hierarchy. And that completes week 7, and thank you.